of your dynamics control knowledge. So we want to be able to establish what sort of control a servo valve would be required. So I'm going to sketch that piston again. That piston has a surface area over here. Surface area is A. So it's going up in that way. So it can be moving up or down. So I'm going to have my convention downward as Y. And you have that hydraulic line that's coming up. And one of these hydraulic lines is going to my spool. So I'm going to sketch a huge spool over here so that you can see it. So this is one part of the spool, this is the other part of that, and it's interconnected. Okay. It's just one part of the spool. And we have the pressure line that's coming in. I'm going to erase the hole over here. So this is the part. I'm sketching like just what you could see in the previous slide, where this part here is your supply line. So your spool will move up or down in that way, depending on the armature. So this distance over here, that distance, I call it X. And this X is what we call the spool displacement. So the spool displacement, originally in the neutral position, your X would be 0. And as you move the spool downward, then we call that amount of X as your spool displacement. So this size of the opening, the size of this opening X will relate to the flow rate. And actually, there's this changing of the symbol. I know we saw just now it was capital letter Q, but over here it switched back to small letter Q. So this small letter Q in this slide here is the flow rate. And volumetric flow rate activity, so it has a unit of meters cubed per second. So we can relate the this flow rate Q, volumetric flow rate, to X by a constant C. So C is a constant, the constant of proportionality. I call this equation 1. Now, how is it related to X? Well, because X kind of controls the amount of flow rate that you can pass through. So the larger X, the larger amount of flow rate. So then what is that relationship? We don't show here, we put a C. So the other thing is that the length of open time. How much time this X is being open, that time relates to the amount of volume of fluid that will pass through, the amount of fluid that will pass through. So that one means Q dt. Because Q dt will give us the volume. Flow rate multiplied by the time change will give us the volume. So volume in our case, if this were to be energized in that way, in your cylinder, the amount of volume that causes this to move down to the next, causes this piston to move down because it's energized. That amount that has been moved down period multiplied by a small little change in the y movement that downward. dy is from here to here, the amount that you move down. So I take this as dy. So that's the change in the volume. I call this equation 2. So what I could do is to substitute 1 into 2. That is Cx dt equal to A dy. Is Q is Cx. So I could simplify this dy equal to C over A x dt. And hence y will be integrating dy, that is integrating x dt. So using this simple formulation, could you see how the piston is moved down? That relationship. This y is how much the piston is going to move down. It has this relationship compared to your x value. What do you think this servo motor is? Is it a P, I, or D? That relationship. You have done PID. Yeah. So with this relationship, y, which is the amount of displacement that the piston moves down, y relates to integrating x into 2. Is it P, I, or D? So that relationship, that servo motor acts as an integrator. Here is so it's a pure integrator. In your dynamics control, do you remember what pure integrator does to your control? What are the characteristics in terms of its response? You would have this thing that you can use to control overshoot. So the overshoot response of your cylinder, how much you will have overshoot, and the pure integrator, what happens to your error? Remember? For an integrator, the integrator actually will accumulate your error. That's the pure integrator. So, in short, your amount of x, which is your spool displacement, x is controlled by your servo motor. And how it relates to the servo motor is that the current controls the position and the duration of the current. That means when you apply the current, how much time you apply it, you will control the rate. And the servo motor itself is actually an integrator. That's an insight for the school. So the spool will get a command in a way from the servo motor to move up or down in this case. And for a simple robotic, you can actually use this concept actually related to the hydraulics. There are actually some Lego that comes with the pneumatics, so you can use that for playing with a toy, knowing that your servo valve is an integrator, you can use that to control strategy. Although the spool is controlled by a servo motor to actuate it up or down, there's also another kind of actuation that's done by lever. So it's actually easier to have a look at how this is done through the animation. So I have this animation that talks about how the spool can be actuated using a lever. Let's see where it works. Okay. Alright, this is a spool. I highlighted it in red color. And there's a load that's acting on the piston. And this part over here is a cylinder. So the cylinder is actually connected to this blue line over here that's called a lever. And this joint over here is hinged. So as this joint over here is hinged. So this lever over here would be actuated if you were to push it or lift it upward. So I'll let you watch this animation twice. So the first one is that you have the actuation, you lift it up. So you can see that the spool starts to move upward. So when the spool starts to move upward, you'll find that this top part over here will get energized, and hence the load will be pushed downward. So as the load will push downward, you're going to see that the whole system behaves in the following way. And it pushes it down together again. So that pushes it down is actually a way to correct the amount of error signal. It's kind of like an error signal strategy. Now I'll have the animation for you to see. Okay. So it starts with this. So over here, you will apply your lifting force. As you lift it, you can see that the spool will move upward. But because it's pivoted over here, you actually don't change much on this piston. And then this part gets energized. And then when it gets energized, you'll push down everything, including the spool because it's connected by this link over here. It'll go down like that. So this is self-correcting here. So you wouldn't let this line be energized continuously. This is connected to the spool. So what's going to happen is that you bring the spool back down because by that time this load would have gotten down to a position and you wouldn't crash down all the way back. So this is one way of error signal. The lever arm is providing an error signal to the system. That's what it means. Now I'll show you a quick video on this kind of bladder design. I think that was done by Pastor. What he has is this oval bladder that's inside the sheath. So the sheath is kind of like a cover, and then there's a bladder over here. So when we energize this bladder, it's going to form a kind of like more circular shape. And when it forms a more circular shape, it can be used to actuate things. So let's have a look at how this is done. It's by the company. It's actually a robotic one. You can see that it's lined with all this ladder system. If you have been wondering, can it be very precise? This is how precise it can become. It's actually very difficult to control a robotic arm movement. So this ladder holes that's around it, they're kind of like muscles, right? Right. And you can see the amount of that one is not very heavy, probably. You can see a lot of holes, a lot of connectors. So your system would be relatively huge compared to an electric motor. You have a lot of these valves that you can see over there. Now, what you couldn't see is behind the box, where is it going to? It's actually going to your hydraulic fluid reservoir. So it's not just that form factor, it's not just that robot. There's a lot of supporting devices behind it. So that was the ladder. You can see that the way that this arm moves is actually not very precise. And not only that it's not precise, it's actually hard to use a proportional valve to actuate it because of the integrator. So that integrator is going to introduce non-linearities in this movement. So it's not whatever amounts that you energize it correspond to a linear response. It's non-linear. That's why you can see that its movement is not very smooth. I have this I'll display the visualizer. This part. Now, just now, one of your peers was asking me, when we look at this circuit over here, right? There isn't this accumulator, so where is the accumulator? Where are the rest of your filter? Where is it that you put everything in? So this is an electric motor, this is a hydraulic power unit. And if I were to put everything into perspective, again, this is your motor, it's supplied by your electricity, and then that's where your compressor is. So your hydraulic or pneumatic system will be energized by your electric motor. Where the inlet is going to come in, especially for this case, we are referring to a pneumatic actuator system. So for a pneumatic actuator system, your airflow is going to come in, and because it's your ambient airflow, you need to filter it And then because the airflow that's coming in that is supplying to the compressor, so there's a gush of airflow that needs to come in order to supply that amount of pressure. So you need a silencer to come in between so as to reduce the noise. So this part here will reduce the noise because of the large amount of air inlet. And after being compressed, it will move on to the pressure relief valve. And the pressure relief valve is in a way to protect against the abnormal increase or decrease in the pressure due to your compressor. Because your compressor is not going to have any intelligence, it's just going to run continuously. You wouldn't be able to run so as to supply you with more pressure, less pressure, no, it's just because there's no feedback. So in that case, you may experience increase or decrease in the pressure. So your pressure relief valve will be able to relieve that increase in pressure out to the atmosphere if there's an overpressure. And because when air has been compressed, what's going to happen is that it's going to increase its temperature. So you need a cooler over here after the compressor, cool it back down to the normal room temperature. And after it's being cooled down, we need a filter and a water trap because there's going to be condensation. So it's going to remove the condensate over here. And it's going to filter off the water, right, the condensate, which is water. So this air receiver will increase the volume of the air and correct small pressure fluctuation. So this, in a way, is like your accumulator. And once after all this, then you'll pass through your proportional valve, and then you'll go on to whatever actuation that's required. So this kind of like completes the entire signature. So that's all I have. Today we end early. I'll see you on Friday. And then she is here if you need.
I can do it.